So today we have looked into the propagators of the fermionic field and the edge field. Today we shall once again look back into real scalar fields and discuss one more thing that I want to tell you, and then we shall move into fermionic fields and interactions between them. So let us start with these, with the discussion of the real scalar field. So let us look at the 2-point propagator once again. So you remember that this was the 2-point function that we calculated, and this was basically nothing but the VET, the vacuum expectation values, the time order product of two real scalar field operators, which are basically, and now we are considering the scalar field operators in the full interacting theory, and this was basically the vacuum expectation value of the time order product of those two real scalar field operators, and the vacuum is the full interacting vacuum. And there we calculated this, and what we found the result was x1, x2, propagator, and then we had x1, x2. So after one loop or the vertex here, this was our data. So if you remember that in diagonal form, the result for the 2-point function we calculated was this. What we shall do today is we shall concentrate on this diagram, and let us calculate this diagram once again. We had already written down the expression for that. So we have this thing, and if we apply the Feynman rules, quite straightforward to apply the Feynman rules, then what we shall get is the following. For this vertex, I will have a minus I lambda factor. Then there will be a symmetry factor for this diagram, 2. Then what we will have is the following: since we have a loop centered at x, if I call this point x, then for this loop I will have the I that is 0. This is a Feynman propagator. And then the vertex has minus I lambda. The position space Feynman rule tells us that we will have minus I lambda, and then with an integration over this space-time point, integration before x. And then there are two internal lines or internal propagators. What we shall have is I delta f x minus x1 minus I delta x minus x1. So a straightforward application of the Feynman rules in position space gives us the following mathematical expression for this diagram. What we shall now do is we shall take a Fourier transform of this and see what happens. If I take a Fourier transform, our main goal is to perform this integration over this vertex. So if we do that, so the Fourier transform shall get right from this square So this is basically the Fourier transform of this part, and then we will have another term called the integration over momentum is Q. Before Q is going to be 4 I square. So that is what we shall have. So if we so I hope this is clear. So let us now perform the X integral. Have an I bracket. Then we have these momentum integrals before 5 for 8. Then we shall have what we can do here is we get rid of this that I into I that is minus. Then we have this integration of x, and that is this here. So these parts I can write it down as I one, that part is x2, then we shall have exponential of minus I a plus q dot x. Right? I hope this is clear. Is it okay? So now what we can do is we can perform the x integral. So let me just go to the other side of the board. So if we perform this x integral, so that will give us a direct delta function times a factor of 2.1 to the power 4. So what we should have is, okay, we have got rid of these i's now. So this gives us a bracket. Before q, we have only a factor of 2.1 to the power 4 downstairs, but we have a direct delta function. Then we have x1 by the factors of the propagator that we have downstairs times p plus p. And if we perform the direct delta function now, say perform the q integral over q, then that will give us minus over here, and all these factors will be minus k. So ultimately what we shall have is lambda by 2. That is what we shall have. We could have straight away written down the result using the momentum space Feynman rules in momentum space. That would give you that result immediately. Okay. But it's a little bit different in this case. Can you identify the difference?
Square.
Huh?
Square.
No, there is no difference. It's not the difference. Square it's fine because there are two parameters. So, okay, there is a little bit of difference here. If you notice carefully, all of these online guys also please notice this carefully. When we apply the Feynman rules in momentum space, you don't have x1, x2 here, right? These are basically like momentum, a particle comes in with momentum and then goes away. And then you say that these are the external legs of the diagram. And for the external leg, you put in the factors of that, the external factors that you have, the normalization factors, the plane wave factors, e to the power of these plane wave factors and everything that you need to put. Those are the rules in basically in the position space. Then when you integrate, you basically perform the integration over x, and then all these factors basically go away. If the exponential, these factors go away. You don't have these factors because we have integrated it out. So that is the difference. Because these external legs are then particles coming in with some specific values of momentum, but here it is not that case, right? This is something else. This is the two-point propagator. So if you just nightly apply the Feynman rules in momentum space, you may get a little bit confused because of the square factor. Because of the square factor, you may get confused. But there are some similarities also. You have loop, you have a loop, and therefore the loop integral comes. But remember, when you convert the things that we have been looking so far, so you can understand the difference between this diagram and this diagram once more in a very nice way. Suppose this particle, we have calculated this is P, and this goes away with momentum Q or P prime, whatever, and due to momentum conservation, for momentum conservation, this and this must be equal. But this diagram is different than this diagram. Because here, there are no x1 and x2. Here, there is an x1 and x2. There is a loop. For every loop in momentum space, you have an integral over d4k by 2 by root to the power of 4. That is there. But this, for this diagram, we have actually derived the Feynman rules in momentum space. And also, we have you can straight away apply the Feynman rules in position space. But for this diagram, if you try to apply the Feynman rules in momentum space, then there is a problem because here the 2 points are x1 and x2. So it is a little bit confusing if you try to apply the Feynman rules in momentum space directly for this diagram. So you should be careful here. So the best way to do is apply the Feynman rules in position space and then just Fourier transform and get this. Okay. So this is a very subtle point. This diagram and this diagram is a little bit different because there is no x1, x2. There is a x obviously here, but then that x gets integrated when you perform this integration. Okay. So what we have obtained is the following. You can see the whole board, I think. So let me again zoom to the top of the board. So what we have obtained is something very interesting. So this thing is basically I delta F x1 and x2. And this diagram, so let me do all the calculations. Do not write this. This is we have to linear order in the coupling constant. This gives us minus 1 by 2 delta F. Obviously, for the loop, you have the momentum integration divided by factor of 2 by root to the power of 4. then we have so this is what this again we can Fourier transform. If a Fourier transform, I will get 4k. So this is what this thing. So always have a factor of I here, this I, and then we have this factor, but you have something in common. So I can take this factor out and then write this as I. So this will be a plus I, that means will be minus sign lambda 2. Okay. That takes care of this term. Then we have straightforward algebra. Now I shall just perform a simple trick. Since we are calculating up to order lambda square, therefore I will just write it as minus e power minus 1. Okay. So that is fine. And then we can simplify this down. This is basically, so if you take the inverse, what will happen is the following. That n square I this full thing after taking the inverse. So this will give us n square. This factor that just tells you that should the whole. So now you can see that this factor cancels with this factor, and therefore you have this equal to k. So your 2-point function up to order lambda is the coupling constant, basically given by this expression. So this is the correction that you get from the coupling constant lambda, or you can say up to first order in perturbation theory, or up to one loop. This is the correction. Now the question is, what does this result tell us? This result basically tells us the following. If you look at the free propagator, you see that this propagator has poles at k is equal to plus minus n, or k0 is equal to plus minus ek. So this has poles here, but now due to the interactions, due to the coupling constant, or due to this diagram, the pole has shifted. Right? Pole has shifted, and this has now this thing. I call this thing as m r square. then both are at this point. Or you can similarly, you can just convert this to K0 plus KP and write it. All right, great. But the poles have shifted, but something, already the poles have shifted, something interesting has happened. So what does the pole tell us? The pole of this tells you about or gives us information about the mass of the scalar particle. So now the coupling constant or the direction that we have incorporated or the first order in the coupling constant tells us that the mass has shifted. Because the pole of this thing gives you the mass of the particle and that mass has now undergone a change. And it is interesting to note that we call this as mr squared, m squared plus I lambda by 2 delta 0. You should remember that this result is valid only up to first order in the coupling constant, not up to higher orders, because higher orders we need to incorporate more terms and then this result will change accordingly. But what is important is the following, is that the poles are shifted to this value now. So this we call as the denormalized mass, or the physical mass of the fluid. Why? Because you see that this mass or this term, the term that we have over here, this is delta H0, which is basically this thing. If you write down the expression for this delta H0, this is nothing but before k by 4 I square. And this therefore diverges for k large or k to infinity. This is infinity. This is quadratically divergent. Right? And therefore the correction that you have to this mass is an infinite correction. So this tells you that the entire program has now, it is a problematic thing that you have some correction. That correction should in principle be small in amount because this get the perturbation theory. But this correction turns out to be an infinite amount of an infinite quantity. And therefore, to avoid such infinities, this procedure is the following. We say that we absorb this infinity in this mass and we call this as a renormalized mass, and this is the physical mass of the particle that we measure in the level. So all the infinities has been absorbed in this mass, and then you have a physical mass. This we call it. And this is the standard procedure of renormalization. But there are, I think we shall not get much time in this course. If we have time, we shall definitely discuss how to renormalize, or is the 5-4 theory at all renormalizable or not? If we have time, we shall discuss those issues. But here, the point is that this shift in the mass which is coming out from this pole is an infinite quantity, and you just absorb this in this thing, and you define the new mass, which is called, said to be K1. The literature it is said to be the renormalized mass, and so everything is, all the infinities have been absorbed. Now the question is that when you go to higher orders in perturbation theory, you can see that there will be more loops, and each of those loops will be, whenever you have loop integrals or loops in your theory, each of those loops are divergent. Therefore, more divergent terms will come here. The question is, can you systematically absorb all those infinities and define a renormalized mass? That is the question of whether a theory is renormalizable or not. And it turns out, at least for 5-4 theory, this is a renormalizable theory because one can systematically absorb all the infinities and define something physical, some physical quantity, and you can systematically do it in up to all orders in perturbation theory. And when the program of renormalization is the following, that you can show that the systematic redefinition of all your parameters in the theory can be done up to all orders in perturbation theory, then the theory is said to be renormalizable. cannot be done, then you say that the theory is not renormalized. So it turns out from the hyper theory, what people usually show is that you can prove it that it is renormalizable up to all orders, but what people usually show is that you can renormalize it at least in books. What is done is the renormalizability of this theory is shown to hold at first order imperturbation theory. That is first order in the linear order in the continuum. So this is something which I wanted to discuss. And another thing which I want to discuss is about the divergence of these diagrams. This diagram, and if you remember, you also calculated diagram like this fish diagram. And we said that this diagram is logarithmically divergent. So we want to calculate the divergence of this diagram. So are there any questions at this point? If you have any questions, you may ask at this point.
Sir,
Ah,
in the first order loop correction, there was a factor of 12 that you have omitted.
which
Why
which factor?
12? There was a factor of 12, I think.
There was a factor
Uh,
of
12.
12. Okay, maybe. So don't worry about that factor. Here the main thing is that this physics is the most important. The main lesson is that the pole has shifted to this value.
Okay.
That is the main lesson. But for this diagram, I think this will not give you the factor of 12. That 12 factor will get cancelled with factorial, right? The 12 factor that you have, that will get cancelled by the 4 factorial that you have in the denominator due to the 5-4 theory. Okay. You have a 5-4 theory, like 5-4 by 4 factorial. This factor will take care of that 12 factor that you had from Wick's contraction, from Wick's theory. And you can actually see here when we wrote down the value of this diagram, we have taken into care of the symmetry factor of this diagram. And the symmetry factor is 2. So how do you get the factor of 2? Whenever you have a loop, that is, you have a propagator which ends at the same point, for this thing you have a factor of 2. This is the symmetry factor of this diagram. So that is fine. That is not a problem. Okay. So now let us discuss the divergence of these diagrams. So suppose we are working in these space-time dimensions. This is the number of space-time dimensions. Okay. Now, as we have seen for this diagram, this is in d is equal to 4 space-time dimensions, right? We have been so in d is equal to 4. This is not d space-time dimensions. So let us read in general. So in 4 space-time dimensions, you see that what is the degree of divergence if I say what is the degree of divergence of this diagram? And if I call the degree of divergence to be capital D, then we can see that each loop basically contributes 4 powers of k, 4 powers of k in the numerator. So if there are n loops in a Feynman diagram, then each loop in D is equal to 4 space-time dimensions will contribute 4l powers of k, right? So in these space-time dimensions, it will contribute d into n powers of k. So number of loops multiplied by the number of space-time dimensions, that will be the powers of k in that particular diagram. But each loop contributes only 2 powers of k to this internal line, right? So if there are I internal lines, so every propagator means one internal line. So every propagator basically contributes 2 powers of k in the denominator. Therefore, the degree of divergence is very simple. It's just d L square, right? Therefore, you can check it for this thing. For this diagram, you have this and say d is equal to 4. So number of internal lines is just 1. D is equal to 4. Number of loops is 1. And therefore, D is 4 into 1. So it shows the validity of this expression, because this one, for here again loop is 1, small d is 4, number of internal lines is 2. Therefore, if you calculate d in 4 dimensions, that's 4 into 1 minus 2. This shows that this is logarithmically direct. Okay? Now, let us.
Sir, what is capital D called?
Capital D is called the. Okay, let me write it over here. It is called the degree. Capital L is the number of loops, capital I is the number of propagators or number of internal lines, and small d is the number of space-time dimensions. So capital D is called the degree of superficial divergence. Okay, it is the degree of superficial divergence. Now, take note of this word. What do you mean by degree of superficial divergence? We shall come to that point later. So now, let us consider the diagram, Feynman diagram. So as I mentioned that in many Feynman diagram, the anatomy is as follows. You will have external lines, you have propagators which are internal lines, you will have vertices, and you will have loops. These are the 4 things that you have in the Feynman diagram. And if you have a diagram with n vertices, so n the number of vertices. So for the 5-foot theory, at least for this kind of a theory, each vertex has 4 lines, right? For 5-foot theory. For 5 to the power of r theory, if your theory is 5 to the power of r, then each vertex will have r lines. Right? 5 to the power of 4, here this is r is equal to 4, small r is equal to 4. Each vertex has 4 lines, and some of the lines will be external lines, and some of the lines will be internal lines, right? And therefore, if you have a diagram which has n vertices, then you will have 4n lines, right? And this will be equal to, some of the lines will be external, so this is 4n will be equal to e, and some of the lines will be internal, and suppose you have 2 vertices, so you have 2 internal lines, but for this, suppose you have a diagram like a fish diagram that we have. Here what do we have? We have d is equal to 2. So there are 2 vertices. So what n is basically the number of vertices. And therefore, how many lines do we have? 1, 2, 3, 4, 5, 6. Okay. So in this respect, just for every vertex you have 4 lines, so this will just give us 8. But that is equal to 4 number of external lines, and these there are 2 internal lines. So if you just add 2, we will not get 8, right? So what is happening is each internal line is getting counted twice. So this is basically 2 into.
Does that absolutely come from the symmetry factor?
No, it is basically, this is not the symmetry factor. It is basically telling you that internal lines can get connected to two different vertices, and therefore the counting will be twice. So what you are doing is these two vertices, here you have two vertices. So you are saying that you have eight total number of lines. But when you say that this is 8, then if you start from this vertex, it's 1, 2, 3, 4. But then when you are saying that this is another vertex and count it as 1, 2, 3, 4, then you are over counting the number of internal lines. And that is why you have the factor of 2. So this is another important relation between the number of vertices, the number of external lines, and the number of internal lines of the properties. So this is also something important. And now let us come to, suppose we have a diagram which has n number of vertices. So if you have n number of vertices, then there will be momentum conservation at each of these points, and there will be overall momentum conservation for this diagram. Therefore, there will be n minus 1 number of relations among the momentum, because momentum conservation at each of these points, overall momentum conservation, therefore n minus 1 relations between the momenta, and the number of independent momenta will be given by number of internal lines I minus the number of relations between the momenta. This will be the number of independent momenta, and that is equal to, you know that every loop, if you have one loop, the number of independent momenta is 1. Therefore, the number of independent momenta is basically equal to the number of loops. So this is another relation between the number of loops, the number of vertices, and the number of internal lines. So we have one relation over here.
So what is n minus 1? Can you repeat?
N minus 1, suppose we have a diagram with n number of vertices. N minus 1 is the number of relations that you have between the momenta. It is the
Number of relations.
number of constraints, the constraint equations, or the number of relations that you have between the momenta. Why it is n minus 1? Because for each vertex you will have a momentum conservation, but then there will be an overall momentum conservation. So for each vertex, there are n then the momentum conservation. So for n vertices, there will be n number of momentum conservation equations, right?
Yes.
But there is an overall momentum conservation, and that reduces the number of equations from n to n minus 1. So there are now n minus 1 equations between the momentum. Okay?
Yes.
And if the number of internal lines is I, each internal line you can attribute a momentum to every internal line, but not all the momenta are independent. So how will you calculate the number of independent momenta? So number of internal lines minus the number of relations between the momenta will give you the number of independent momenta. Okay, and that value is I minus n minus 1. And that is basically equal to nothing but the number of loops, because the number of loops is basically equal to the number of independent momenta. So you have this relation. So there are three relations that you should keep in mind. You have this, and you have the degree of superficial divergence. So what we can now do is we can substitute L is basically I minus N minus 1. So this is this thing, and then you can also substitute the value of small n, or this is minus 2i. So what you can do is you can substitute this thing over here, and then you can try to get an expression for capital T. So if you want me, I can. If you want me to do it, I can just calculate it for you. Let us do the calculation. Now stop. So what we have is D is equal to, or D L 2I then equal to D. L is 1 side minus 10 2i. And you just need to do the algebra. If you do it, this will give us b I minus n into b 2i. Then I think we need to substitute. So this is d minus md. Yes. And okay. So this is d minus md. This takes care of these two terms. Plus this is d minus md di d minus 2 I. So that this, but I from here, from this relation is I is 4n e by 2. You can just substitute what I is from here, 4 n minus e 2. So cancel. You can just simplify this further, and your final expression that you will get from here is the following. It will be d minus d by 2 minus 1 e d by 2 1 e plus this will be the expression for degree of superficial divergence. So I shall continue from here in the next class. But this is the expression for the superficial divergence of this diagram. You can check it. You can play with this for these two diagrams. For this one, I grabbed it. For this diagram and the fish diagram. So you can see from this expression that when d is equal to 4, this term goes up. So what you have is 4 minus 4 by 2, that is 2 minus 1, so this is 4 minus e. So nice simplification is for d is equal to 4, capital D is 4 minus e. So you can immediately see that for this diagram, number of external lines is 2, so this is 2. For the fish diagram is 4, it is 0. So your formula is correct. This is the formula for 5-4 theory. Okay. So everything works out well, but then we need to discuss some finer points about this. So that we shall do. Why is it called the degree of superficial divergence and why not degree of divergence itself? We shall discuss those points in the next class. So do you have any questions at this point?
What is the negative value for this?
Huh?
What is the negative
It is not
value?
divergent. It's convergent.
So if we get d is equal to 2 dimensions.
Small d.
Yes, small d
Okay.
is equal to, that gives us 2 minus 2n.
Correct.
So this is 2 into 1 minus n.
Yeah, you just need to calculate. So this will be 2.
Yeah, 2 minus 2n, that will vanish.
This will vanish.
Yeah.
Yeah.
That gives us 2 into 1 minus n. So n should be greater than or equal to 1, right? So everything converges. So 2 dimensions, everything is converged.
So it is 2 minus what?
2 minus 2n.
2a. So for n is equal to 1,
There is a logarithm.
there is a logarithm. And then there are no divergences. Only divergence that you have is logarithm. So we shall actually discuss those points in the next class. It's a nice thing that we have. The degree of superficial divergence, y is equal to superficial, and what happens for d is equal to 4, what happens if d is not equal to 4, what happens for other theories, for example, phi cube, Phi to the power of r in general we should discuss. So let us stop here for today. We shall continue from here on Wednesday.